Hi girls, today we're going to continue with Haykal and we're going to start with lesson 3. Lesson 3 talks about electric and magnetic field in space. So let's go to that section. You can see previous sections in different videos. Alright, in lesson 3 we have these 3 objectives. Apply the wave equation to calculate the wavelength, frequency, or speed of electromagnetic waves. Question 8. Calculate the speed of electromagnetic waves in different mediums or different dielectric constants. And number 10. Determine the optimal length of orientation of an antenna for the best reception of a given wave. Starting with the first objective, the speed of an electromagnetic wave in vacuum is approximately 3 times 10 to the power of 8 meters per second. It is denoted as c, and it is commonly called the speed of light, c. So all electromagnetic waves, regardless of which kind, they all travel at the same speed in space, which is 3 times 10 to the power of 8. And we call that speed, that number, the speed of light. But all other electromagnetic waves have also the same speed in space. The wavelength of an electromagnetic wave, its frequency, and its speed are all related using this equation. The wavelength of the electromagnetic wave measured in meters, and if you remember from a transverse wave, let's say that this is the wave we have, this is the electric field. The distance between a crest and a crest is a full wavelength. Similarly, the distance between a trough and a trough is also a full wavelength. Or the start of the wave here and ending here, this is also a full wavelength lambda. It is equal to the speed of the wave. This is the speed of the electromagnetic wave measured in meters per second, divided by the frequency of the wave. Frequency is a measure of how many oscillations we have in 1 second. The more oscillations we have, the higher the frequency of the wave. So for example, this wave right here has a higher frequency than this one right here. Frequency is measured with a unit hertz, where hertz is equivalent to 1/second, or second to the power of -1. In vacuum, we said that the speed of the electromagnetic wave is equal to c, the speed of light. So the equation becomes lambda equals to c divided by f. Now it's very important that we memorize this table. Most importantly, the mega, the kilo, the centi, the milli, and the micro, as well as the nano. For the second objective, the velocity of an electromagnetic wave in a dielectric material is always less than that in vacuum. So, for example, when light travels from space to Earth, it travels through air and the speed of light decreases. We can find the speed of any electromagnetic wave in any dielectric, where dielectric means عازل, using this equation. The speed of the electromagnetic wave inside a material or a dielectric material is equal to c, which is the speed of the electromagnetic wave in space, 3 times 10 to the power of 8, divided by the square root of k, where k is the dielectric constant. And it is unitless, it doesn't have any unit. For space, K is 1. For air, K is a little bit more than that. It's 0.00054, I suppose, or 445. Let's say it is 54. You can check from your book how much is K for air. So each material, for example, for water, K is 1.77. Each material, each dielectric has a different dielectric constant. For the third objective, which says the orientation or the best orientation and length of an antenna to receive an electromagnetic wave. Now, the electron's acceleration inside the antenna would be largest when the antenna is parallel to the direction of the electric field. So, you can see here that the antenna spans this axis right here. It is parallel to the electric field that the antenna is designed to receive. So the electron's acceleration is largest and the antenna works best when the antenna is parallel to the direction of the wave's electric field. Also, the antenna is most efficient when its length is half of the wavelength of the wave it is designed to detect. So the length of the antenna L, measured in meters, must be half of that of the wavelength, measured in meters as well. They can be measured in centimeters for both of them, but they have to be the same unit. So you can see here the wave has a wavelength of lambda. L, which is the length of the antenna, has to be half of that, half of lambda. Let's solve these questions together. What is the speed of an electromagnetic wave traveling through air? You see as 299,000 this is 200. You see as this much. Okay, so in this case, he gave me C, not 3 times 10 to the power of 8, but a very close number. This is the actual length, or this is the actual speed of light without the rounding. So he wants me to find the speed of an electromagnetic wave traveling through air. Now, for air, the speed of the dielectric constant in air is 1.00054. So K for air is 1.00054. To find the speed of the electromagnetic wave V in air, I will divide the speed of the electromagnetic wave in space over the square root of K. So 299.792458 divided by the square root of 1.00054. Use the calculator. 299.792458 divided by the square root of 1.00054. That's going to give you 299.711.546. So 299.711.546. Point something, just 0.8. The speed of light traveling through a material is this much. What is the dielectric constant of the material? So he gave me the speed of light inside the material V, and he wants me to find the dielectric constant K. In this case, we'll put the equation C over the square root of K, and then substitute what we have. We have V to be 2.43 10 to the power of 8 equals. C is 3 times 10 to the power of 8, approximately. This is an approximation of this number, divided by the square root of K. Using the Shift solve on the calculator, you can find it easily. All right, so let's put that here. 2.43 times 10 to the power of 8, and then equal, and then fraction, we have 3 times 10 to the power of 8, and down here we have the square root of k, which is the unknown, so we're going to put x, and then shift calc and equal. So k is 1.52. Of course, you can rearrange by squaring, or first of all cross multiplying, squaring, and then dividing. Water has a dielectric constant of 1.77. So this is K for water. What is the speed of the light in water? V equals to see the square root of K, 3 times 10 to the power of 8 over over the square root of K, which is 1.77, using the calculator. So 3 times 10 to the power of 8 divided by the square root of 1.77. It's this much. You can write it 225, 493, 808. 245, 225, 493. And then 808. Have point 4. Point 4. A radio signal is transmitted from Earth's surface to the Moon's surface 376,290 kilometers away. What is the shortest time a reply can be expected? So here, he wants me to find the time. Remember that the velocity is equal to the distance traveled divided by the time. If I want the time, I will say the time is equal to the distance traveled divided by the velocity by rearranging the equation. So I have the distance, but I don't have the velocity. So we need to find the velocity of this signal first. Well, since this signal is transmitted from Earth to the surface of the Moon, so this signal is in space, and in space, the speed of the electromagnetic wave is 3 times 10 to the power of 8. Right, so we have the speed and we have the distance, so we will divide. T equals. So the distance for the signal to go from Earth to the Moon and back is twice this much. So we're going to multiply 2 times 376,290 times 10 to the power of 3. Here I multiplied the distance by 10 to the power of 3 because we have the kilometer, and I multiplied it by 2 because the signal needs to go all the way to the Moon and back. So that's twice the distance. Divided by the speed, the velocity of the electromagnetic wave in space is 3 times 10 to the power of 8. Using the calculator, 2 times 376,290 times 10 to the power of 3 over 3 times 10 to the power of 8, it will take 2.5 seconds. What is the wavelength of green light that has a frequency of this much? To find the wavelength of light, we need to divide C over the frequency. C is 3 times 10 to the power of 8, and the frequency is 5.7 times 10 to the power of 14. Using the calculator, That's going to give you 5.2 times 10 to the negative 7. That's because we have 5.26, so it's about 5.3 times 10 to the negative 7. An electromagnetic wave has a frequency of this much. What is the wavelength? So again, the same way, you will divide C over F and find the answer. What is the frequency of an electromagnetic wave with this wavelength? In this case, you will rearrange the equation or shift solve it. Here he gave me the wavelength. It is 2.2 10 to the power of negative 2. And the unknown is the frequency. So you'll shift solve it on the calculator and find F. So 2.2 times 10 to the negative 2 equals fraction 3 times 10 to the power of 8 divided by x. And then shift calc equal, or of course you can rearrange. It's okay, I have an old calculator, that's why I can't solve. So the frequency is cross multiply, the frequency is 3 times 10 to the power of 8 divided by 2.2 times 10 to the negative 2. So 3 times 10 to the power of 8, 3 times 10 to the power of 8 divided by 2.2 times 10 to the negative 2. It will give you 1.3 times 10 to the negative 10, 10, 10, 10. 1 point, 1.3, 1.4, 1.4 times 10 to the power of 10 hertz. We have these essay questions. Radio antennas normally have metal rod elements that are oriented horizontally. From this information, what can you deduce about the directions of the electric field in the radio signal? Remember, we put our antenna parallel to the electric field. So in this case, the electric field is also horizontal. So the electric field must be horizontal, same as the direction of the antenna. What are the advantages of storing and transmitting sound, pictures, and data as digital signals? Well, that's because digital signals can be stored reliably in computer memory and sent over long distances. They can send more information in the same amount of time as AM or FM and are less affected by noise. Would an FM antenna designed to be more sensitive to stations near 88 MHz be shorter or longer than one designed to receive stations near 108 MHz? Explain your reasoning. Well, it would be longer, of course, because lower frequency. So this is a wave with high frequency. You can see that a wave with high frequency has a small wavelength. This is a wave with a lower frequency. So here we have high frequency. Here we have low frequency. You can see that the lower the frequency, the longer the wavelength. So here, because we have lower frequency, we require an antenna. Remember, the antenna has to be half of the wavelength. Since the wavelength increased, the length of the antenna will increase as well. So the antenna used or designed to receive a signal of frequency 88 megahertz is going to be longer because it has lower frequency, and it means that it has longer wavelength. So they use a longer antenna. Here would have a shorter antenna.